Robotics has fascinated people for years. After the industry, robotics has also reached our schools. Fundamentals of the robotics can be found in the curricula of both technical universities and the secondary schools. We have decided to build our own educational robot that would cost only a fraction of the price of an industrial product, but at the same time, would have similar functionalities. Along with the robot, we had to prepare a control application that would meet our expectations and be functionally similar to the applications used with industrial robots. This is how the RobTrain robot and the RobLAB control system were developed. In the last few years, we have made several changes to the design of the robot that improved its reliability and durability. We have also completely redesigned its controller by fitting it with a more efficient processor, a good-looking housing, and a new functions. Also, the RobLAB software was thoroughly modified. We've added several new useful functions, made some aesthetic changes to the interface, as well as improved the stability and reliability of its operation. Since the January 2016, we have worked on a completely new version of the software. As a result, RobLAB 4.0 is ready and we started to promote and sell it in September 2016. The 4.0 version sets a completely new direction for the development of the RobLAB. We've added many types of robots with the parametric inverse kinematics. Although the previous versions made it possible to build any configurations of the robots and to control them, reverse tasks were possible only in the case of the 5-axis robots without offsets, with all arms straight and in one plane. That means, of a design similar to a RobTrain robot. In the fourth version of the RobLAB, not only performing inverse tasks by 6-axis robots of the PUNA type are enabled, which are standard robots with the multi-articulation arms, but also by robots of the other popular designs, like Skara, Delta, as well as Cardassian, or Portal robots. Parametrization of the definition of a robot selected from the template of the design makes it possible to adjust the shape and dimensions of the robot in the virtual window of the application to the actual arm connected to our controller. Thanks to the 3D printing, better access to milling or laser plotters that facilitate manufacturing, many robot arm designs appear and many people decide to build their own robots. These robots are more or less precise, they meet the expectations of their designers, or are modified and improved many times. However, they still require appropriate control systems. Even the most accurate and rigid arms are nothing but manipulators, without autonomous control systems, just like the excavator arm, or a crane. Using popular programming languages, such as C++, JavaScript, or Python, is certainly a good exercise for the brain, but it's not a good way to teach programming of industrial robots. Programming of industrial robots is done with dedicated tools. This is why RobLAB uses the MELFA Basic language, which is used to program Mitsubishi robots. In addition to standard applications, such as handling, pick and place, robots are used more and more often for specific production operations, such as welding, laser cutting, plasma cutting, gluing, etc. Consequently, it was necessary to standardize the languages describing the movement between CNC machines, which are typical production machines, and robots, which are new in the production area. Recently, manufacturers of industrial arms have been adding the possibility to control the arms using the ISO 6983 language, the popular G-codes. Also, companies that produce CAM software write post-processors that enable controlling robot arms with G-codes. We have decided to enable the RobLAB to support the basic functions of that language, so that the user can become familiar also with this technique. Another technique to teach robots movement sequences that is becoming popular is the so-called drag and teach technique, which is not parametric programming but instead consists in dragging the robot's arm into position and memorizing the posture. Although the RC servo drives that are used in the didactic robot designs do not enable teaching physical robots using this technique, we have decided to introduce this method in the virtual environment so that the users can become accustomed to it. In order to stay abreast with the latest technological trends, we have introduced all of the aforementioned modules. As a result, the user can compare the pros and cons of various methods of programming of industrial robots, and write programs that use any of those methods, or use them in conjunction as required. The robot's controller and the application itself have an additional I/O module that can be used both from the software level and manually. This additional functionality of the application enables not only controlling the robot's arms, but also cooperation between the robot and actuators, signaling devices, such as transmitters, valves, motors, push buttons, indicator lights, and any industrial sensors. This functionality of the application, together with the control system and the robot, allowed us to build and control a MiniFMS production line with a CNC milling machine, as well as the system where two RobTrain robots work along with an industrial Mitsubishi robot. Another example is cooperation with MELFA stations. Currently, not only cooperation by signaling of the position is possible, but also the MELFA modules can be controlled autonomously by the RobLAB application. Also, we made it possible to introduce the model of the MELFA station into the virtual environment of the application. As a result, changed positions can be shown not only using the input and output status indicator lights. In the industry, robot arm operators use operator panels when starting up the robots. In the case of educational robots, where all components and assemblies are located on a table, this is not necessary. However, in order to ensure conditions similar to industrial ones, we made it possible to define points, adjust the speed, or start the program from any tablet or smartphone with the Android system, after connecting to the computer over a Wi-Fi. The software has an exhaustive user manual that not only contains information on how to work with the application, but also makes it possible to learn the fundamentals of robotics. The package includes video tutorials whose parts are shown in this film. The tutorials show how to build virtual robots step by step, how to use the ready-made templates, how to adjust the parameters, and how to write execution programs for the robot. RobLAB 4.0 with the additional educational package is an excellent teaching aid. We encourage you to test the new functions using the demo version of the software, which is available on our website, as an installation file to be downloaded.